Module or Chapter 16, Warning, Alerting, and Monitoring Systems. Okay, modern aircraft rely on integrated warning, alerting, and monitoring systems to ensure timely crew awareness of abnormal conditions. These systems prioritize information, reduce pilot workload because there is too much automation going on, and enhance safety by combining sensor data with alert logic and human-centered display philosophies. In other words, you would have all the possible alarms that you would want to see being displayed on the MFD, the multifunction display, with all the indicators for the engines, the oil pressure, all of that on one screen, usually one extended screen or multiple 2 or 3 screens, okay, for redundancy, and all the warnings or the alarms that you would need, that would be required, or the notifications would be displayed on these screens integrated with the instruments themselves. So you would have an indicator for the engine. Also, in case there was a problem, a warning would fire on that indicator as a LED description, okay, for what's happening on the inside of the engine as an abnormal functionality or something wrong going, okay, as an abnormal behavior, so to speak. You have also the sound, you have the different, like the master caution, the fire warning, all of these displays that are very important in order to give awareness to the crew of the different situations on board, okay, of the different like of the current conditions for the engines, for the cabin, and different compartments of the airplane. Master caution and warning systems. What's the purpose and philosophy? The master warning and master caution systems provide immediate crew attention to unsafe or abnormal aircraft behavior or conditions. The master warning indicates conditions requiring immediate crew action, like a prompt action in order to alleviate, like in order to prevent a more serious, dangerous behavior in the airplane, and to alleviate like the problem promptly and swiftly before it can develop into a more serious, more dangerous situation. Master caution indicates conditions requiring timely but not immediate action. Okay? Now, these systems act as attention getters rather than diagnostic tools. They are only designated to warn, okay, the crew in order so that the crew would act promptly to like rectify the faults and troubleshoot the problems. Activation logic. Warnings and cautions are triggered when monitored parameters exceed predefined thresholds. Okay, the threshold logic. So the alert would be a warning when X is greater than or equal to a critical value, whatever X would be. Okay, so when you exceed a specific operational value, that would become a warning. Okay, but a caution, unlike the warning, like it's a little bit different than the warning, that you would have a specific margin of error, not allowable, so to speak, but it would be less than the warning. So the master caution is when you have a value between two different values, the first one being the first limit, okay, and the second one would be the critical limit. So, for example, when you have a device that starts overheating, it did not yet cross the critical value for it to be a warning. So it would be displayed as a caution. Why? Because let's say the engine had started overheating, it had not hit yet like the critical value that would start causing a damage to the engine, and that would lead to a fire, okay, to an engine backfire. However, the value had stepped above a minimum threshold where it started to become more serious, but it's still less than the critical, the X critical for it to qualify as a warning. So it entered into a precarious margin between the first limit, which is like a start of a or a development of a serious problem of overheat, but below a critical value or threshold where it would be considered, for example, as an engine fire starting within like the engine housing. System architecture, the master alert system integrates sensor inputs, system computers that analyze these inputs, visual annunciators like, for example, the master caution alarm and the visual indicators within the cockpit. And you have the auto alerts like the sounders and the horns that would sound a specific kind of frequency in order to bring the crew to attention, okay? To trigger the crew alert. Redundant channels improve reliability, so you would have R is equal to 1 minus R1 times 1 minus R2. These redundant channels would improve the reliability of the sensing device and the detection mechanism. So when you would have more than one system, more than two systems actually running together to detect the same thing, you would have more reliability and the detection would be more trustworthy, okay? The detection system. Annunciators and alert logic. Annunciator panels. So annunciators provide system-specific alert messages using lights, text, or symbols. But you have different color coding conventions for that. Okay, based on the convention, so the red would indicate a serious warning. That would be like the highest kind of alarm, the most serious, crucial, or dangerous type of warnings or alarms would be a warning designated by a red coloring. Second to it, you would have an amber indication, which means caution. So the difference between the warning and the caution, as we mentioned before, the warning is when a specific value X exceeds the maximum allowed threshold. Okay, so it becomes very serious, like when the fire breaks out in the engine. Meanwhile, the caution is during the engine overheat, the X value would be above a specific value, which is the minimum value, so as to designate it as a warning, like a serious problem, but below the like a designated value for fire, okay, but below the maximum allowed value of heat to like acceptable value of heat before the warning fires off. Okay, so the caution would be when the X value is between a minimum critical, okay, above the minimum critical, but below a maximum acceptable. That would be the most dangerous threshold. Now, for the green indicates the normal operating conditions, and finally blue would be advisory. Alert prioritization. Multiple alerts are prioritized to prevent crew overload. The priority ranking should be evaluated as follows. The priority for an alert is a function of severity and time criticality. How much time critical, or in other words, how much an alert cannot wait before it should be fixed. Also, how severe the alert is. Only the highest priority alert is presented orally using the sound buzzer, okay, or the sounding alarm horn. Alert inhibition and logic. Alerts may be inhibited during certain flight phases to prevent nuisance warnings. Inhibition logic example, when the alert is equal to 0, okay, the alert should be equal to 0 if H is less than the H of inhibitance, okay? So the alerts may be suppressed during certain flight phases because they don't make any sense in such case. So they should be inhibited, okay, because they present a nuisance and a distraction for the crew. Alert confirmation and filtering. To avoid false alerts, systems require persistence or multiple confirmations altogether, summed up in this integral, Okay, this integral function would sum up multiple systems, or multiple confirmations coming from different kinds of sensors, different types of measurements, in order to verify whether the alarm is valid and true, or if it is a false alarm. So the sum of all confirmations should be greater than the X threshold. It is the sum of multiple confirmations, multiple sensor measurements that had led to these conclusions on different instruments at the same time, on different measuring sensors. So the sum of all of these indications in a specific period of time or during the time of detection should be greater than the X threshold that is needed in order to fire the actual alarm in the cockpit. So you might have different measurements that don't add up at times, you won't have an alarm. But when different sensors that are measuring the same thing from different angles come up together and they sum up to a value that crosses the threshold of detection, that would be validated as a true alarm, okay, as a serious problem that needs to be indicated in the cockpit. Meanwhile, if you have only one sensor acting up, other sensors that are measuring the same thing, they are not giving that result, in such case you would suspect that this is a fault in the sensor itself, not a real warning or a real event that is taking place, because sensors are prone to short circuiting, they are prone to false measurements, or if they break up they would also signal a false alarm. 16.3 EICAS and ECAM overview. EICAS is the engine indication and crew alert system. ECAM is the electronic centralized aircraft monitor. Okay, now for the EICAS or engine indication and crew alerting system, the EICAS integrates engine parameters altogether and alerting into a centralized display, commonly used in Boeing aircraft. The monitored engine parameters include N1 and N2 speeds or rotations, which is the RPM percentage of N1. For N1 is the low pressure compressor, which is at the beginning stages of the engine. N2 is the high pressure compressor, which is a high pressure blade compressing the air against a stator blades in the middle of the engine. Okay, they have like small ventilations between the blades so as to guarantee a higher pressurization of the intake air on the inside of the engine to lower its to condense it, lower its temperature, so that when it combusts it would expand so quickly, creating an efficient thrust. Second indicator is the EGT, or the exhaust gas temperature, by which you would measure the temperature of the gas exiting the hose of the engine. 3, fuel flow, which measures the flow rate of the fuel. And 4, the oil pressure and temperature. Okay, because a low oil pressure would indicate a malfunction or a rollback in the engine. And temperature of the oil is also very important. The engine parameter limits should be between X normal and X max, okay, before an alarm would start being sounded, okay, before a notification appears in the cockpit. The ECAM, or Electronic Centralized Aircraft Monitor. ECAM used in Airbus aircraft provides both alerts and associated procedural guidance. Okay, so the ECAM logic: alert would lead to a procedure display, okay, in order to inform the crew on how to rectify the problem. You have system pages automatically present relevant information to the crew. It's like a checklist that is displayed by the computer on the screen. Alert levels: you have level 3, that would be a warning, red, very serious alert. Level 2, that would be caution, okay, amber color. And level 1, that is advisory and white, meaning only informative but no no serious problem is taking place. For example, if we look at the right display here for the ECAM, so you have flat control, okay, so you have slow spoilers, you have the hydraulic B reservoir overheat, meaning a hot temperature in the hydraulic B reservoir, and B system low pressure. Also, the failure message is a low pressure in the B reservoir hydraulic system. Okay, now flat control. So this hydraulic low pressure is affecting the spoilers. Okay, so you have a low control of the spoilers. The spoilers, which are the air brakes, require hydraulic pressure in order to be deployed. So because of the low pressure, which is due to a reservoir hydraulic overheat, this is leading to a low spoiler or slow spoiler deployment, okay, or flat control. Crew interaction, the crew response time is critical, so the time of the response should be less than the allowed time to wait before taking action. Why? Because it is required to promptly jump into the checklist and to, swiftly rectify the problem, especially when you have a critical fault in the aircraft. Acknowledgement silences oral alerts but does not clear the fault. So, okay, so the crew response, it would acknowledge silence, oral alerts, and it should not, like, they should clear the fault after that. Okay, so the time of response or the time allowed, that would include from the time when the alarm is sounded until the time that the crew should start responding to the fault. Now, response time is by definition the acknowledgement silence all the way to rectify the fault. Now, in this display, lower display, you have, for example, landing gear is inhibited, okay, during flight, APU bleed, okay, you have no alarms here, just indications. This is the quantity of oil, fuel that has been used, okay, CAS, cabin VAS, okay, feet per minute, altitude of the cabin in feet, which is 4,150, indicating the pressurization of the cabin, okay, and different other measurements as well. 16.4 Human factors and situational awareness. Human factors considerations. Alerting systems are designed with human limitations taken into account, okay, in mind, including the attention span of a person, the reaction time that needs to be invoked in order to rectify and troubleshoot the problem, and workload, meaning a person cannot focus on multiple things, especially if they are taxing if they are taxing work assignments, he cannot focus on multiple things at the same time to effectively do them all. Okay, and situational awareness or SA consists of 3 levels. Okay, what are these 3 levels? Perception of elements, comprehension of meaning of these elements being involved, and projection of future status. The situational awareness effectiveness is equal or is a function of I, C, and T, where I is the information quality that's being displayed on the screen. C is the cognitive processing. Cognitive processing means that the person is understanding the data that's being displayed and what it means. Okay? And a function of time, meaning the time that it takes the crew or a pilot in order to read the data that's being displayed on MFD, for example, or ECAM, be able to also process that data and drive from it a meaning, okay, like a an analysis and an assessment to the current situation. So T is the time that it would take the pilot in order to understand and read these parameters and to analyze what these parameters actually mean. So again, another thing that from these parameters, when they are analyzed by the pilot, he can project for future processing, meaning he can understand what the airplane is going to do next, especially when you have, for example, an airplane during a climb. He would understand that at this speed you would have a stall. Outside of this speed, you would be safe. So he needs to, so that he would lead the aircraft to guard specific margins of airspeed, of angle of attack, in order to enhance the performance of the entire flight. Workload and information management. Pilot workload increases with alert frequency. Okay? When you have multiple alerts, the workload for the pilot becomes so unbearable at times. Proper alert filtering reduces the overload and the overwhelming of the pilot. So the number of presented alerts should be less than the number detected, so as to represent aggregated alarms, okay, in a way that the most crucial alarm would have a priority, okay, and a precedence over the less critical alarms. Also, the alarm from which other problems would stem, that root alarm would be displayed first and foremost. Let's say, for example, to give you a simple scenario. Okay, so in your house, let's say the power is cut and you have different sensors connected to your TV, to your fridge, to other utilities within the house. So all of these would go down. Can you imagine the amount of alarms that you would getting from your telephone, from your TV, your microwave, your fridge, okay? But all of that become very distractive to the person. Why? Because the root alarm is a power cut. So the alarm that has a priority over other alarms should precede and should be displayed first, and should be the glaring alarm on the screen. Okay, because all the other problems stem from the very first main alarm, which is the root cause for other systems being shut down. The design philosophy: modern alerting systems follow principles of consistency, clarity, meaning the alarm should be clear, the indication should be readable, clear, and understandable. It should make sense for the pilot and to give him an idea of understanding over what situation has came up and what is going on within the aircraft. Okay, now prioritization, meaning again the alarm that is most serious should be displayed above the other alarms that would stem from that very same problem. And also minimal distraction, which means using the alarm that is the most important and crucial to be solved first in precedence to other types of alarms. Finally, warning, alerting, and monitoring systems combine reliable sensing, intelligent alert logic, and human-centered design to maintain crew situational awareness and ensure timely, effective responses to abnormal aircraft conditions. Also, if I may go back to the previous slides here, when we've spoken about consistency, what does consistency mean? So consistency is that the alarm is always reproduced in the same manner. Okay, so whenever you would have a problem of that same sort, the same alarm would be displayed. That would be the consistency, and in a consistent way. So it's not like at times detected, but at other times it would be missed. No, there's an importance for consistency in the display and the display analogy, and also the clarity of the display and what each alarm actually mean.